Yeah, hello and welcome to our presentation. My name is Alexander Mattes from the Kiel University of Applied Sciences. And yeah, as introduced, I present to you an approach for injection molding tools. Could be also applied for die casting tools, where we use DED, powder DED, for introducing conformal cooling channels into this kind of tools and combining it with multi-material, so with a material which is very good in heat transfer to actually reduce the cycle times. And getting a bit to introducing our research group, we are dealing with all kinds of manufacturing technologies, starting from the machining, overforming technologies, welding, and of course additive manufacturing. And we are focusing on combining this with artificial intelligence, with data science for process monitoring. So this is a field where we at the moment also expand to other additive manufacturing technologies like wire arc, also friction stir welding, as well as powder bed. So getting to our use case I'm presenting today. So actually, in the injection molding business, it's all about uniform cavity, temperature, and high cooling rate. This combination, having a unified cool down of the part and having a fast cool down of the part. And actually, we are talking about this one. We want to reduce the cooling time by actually reducing the complete cycle time. And one approach is, like you see here, conformal cooling done by powder bed fusion. But what you getting hard to do with powder bed fusion is getting into the multi-material and functional graded material approaches. And our idea, our basic idea, is having an injection molding tool with conformal cooling, but combining it with functional graded material, having here a seamless transition from a very a material with very high heat transfer coefficient to a material which is a classic tool steel, which has a very high stiffness. In doing so, we think direct energy deposition, powder-based, is a very good choice for it. And what we want to do this in the future is to combine it with powder bed fusion, because in a short summary, powder bed fusion, you can do very precise, very thin layered parts in a limited dimensional area with a limited size. In comparison, the direct energy deposition can do multi-material in these areas where you need it, because you can build up on existing parts. And combining this, we are also at the moment currently starting a research project in that area. So if you are interested in this, we would be happy to discuss it with you. But this has been the basics so far, and here just a showcase how precise we can get with our add-up beam modulo 400 machine tool. So this one is a transition from 316L to copper alloy 10 with 2% stages in mixture from layer to layer. And we used actually the copper aluminum to also optimize the tool I'm showing you now, in which we haven't used functional graded material. We already achieved a huge benefit just by using multi-material. So what we did is actually together with the company Nissen from Tönning in the far north of Germany, they are actually producing road safety solutions. So all of this, including the conveyor, is produced by them. And they have just a problem here with this kind of part. It's just, you know, a cover, a connector, which you can put here at the corner edges. And they have a problem with cooling down time coming from the core. And what we did is actually here we used this core and transferred it to an additive manufacturing part. It was it was electrical discharge machined up to now. We first transferred it to produce it, to be able to produce it with additive manufacturing. We try to avoid 5-axis machining as much as possible. I show you just why. to simplify to 3-axis toolpath, but at some points, you see the conformal cooling, we had to go to the 5-axis. And just to show you what that means, so you have here 1 millimeter allowance between the part and the nozzle. So a bit tough job for the NC programming. So this is also part of the story, so that you have to simulate this first. You have to have some smart programming strategies, CNC strategies. But in the end, the outcome was a tool core made out of copper alloy. You see here, we have just milled it up that you can look inside. You see here the surface quality of the internal coolings. It's fine enough for having a sufficient cooling. And you have, due to this combination of tool steel and built on it up a core from copper alloy, you have a tool which much better heat transfer, with much better heat transfer characteristics. And now I think this is the really interesting part for you. What was the outcome? We could reduce the cycle time by nearly 51%, over 50%. Because with a conventional tool, we had a demolding temperature by 100 degrees. We could go up with a demolding temperature up to nearly 130 degrees, just limited by the plastic material which is used. Actually, if you are interested in seeing the results, we can show you in a separate way. We haven't them here at the moment, but we can show it to you so that you see the parts are still maintained from the quality requirements, so no differences, and really getting a significant benefit here out. Still, if you look here, if we maintain the demolding temperature, this is how it is currently used at Nissan, because they wanted to stay out of, they want to have a safety margin here, so they are staying with the demolding temperature they currently using. You still have 20% improvement in the process, in the cycle time. And what does it mean from a cost perspective? Machine costs reduced also by more than 50%. And you're ending up with nearly 20 cents per part. And again, you could go up to here. You still get parts which maintaining the quality requirements. And even with the more mild approach, more conservative approach, you are still having a significant cost saving. But of course, you have to invest first a bit more in the tool itself. It costs you more because you are machining it not in a conventional way. You're building it up with additive manufacturing. And you see here, I think for most of you, it's very common or very well known. The machine costs of the additive machine tools are the most fraction of it. We assumed a two-shift operation with, let's say, 70–75% depreciation. So to get some realistic numbers behind it. And you see here, you don't need that much high volume for the injection molding part. I think an injection molding part with 10,000 pieces, or if you are at a bit lower demolding temperature with 25,000 pieces, is not that high volume for an injection molding part. So there we can really show you have to invest a bit more, but it pays off for most of the parts, for many injection molding parts. Yeah, and that is actually a bit the outcome, and I'm summarizing a bit. Of course, you get time reduction, but in the end, you get a significant saving in manufacturing cost, and what is nowadays even in the same way important, you get also a much less carbon footprint. And of course, it's a very simple part, but that is even more impressive that we can save a lot with this simple part by investing an amount of money which is you can invest and get back with a certain point, or with a certain point in time, which you which doesn't sound too bad. Yeah, so I was happy to presenting you this technology transfer project. And yeah, if you are interested in the technology, if you are interested in working with us, we are here. Also, my expert, Tore Gericke, who is the co-presenter, is also here asking you any questions, much more in depth I can. And yeah, would be happy to follow up with you. Thank you.
Okay, I have the microphone. If anybody would like to ask a question now, where else can they go? Where can they find you today?
We don't have a booth, actually.
Okay.
But I have my cards with me, so if you want to share our contact information, and we get very good experience having afterwards an online meeting or anything to discuss in more depth. So feel happy to direct speak with us.
Perfect. And in terms of the life of a tool, how does a traditional tool compare in terms of total lifespan?
That's a good question, and I openly have to answer, we haven't tested yet. This is a brand new thing. We don't know how long it will rely, but if you look at the numbers, you just need 10,000 parts to get it paid off. I think from a material point of view, you have good chances that it will last these numbers, also 20,000 parts. So the benefits you get from it, but of course we have to be open. We haven't tested it yet for 20,000 parts. We will have. I can tell you in 1 year from now, maybe.
Maybe we'll see you next year for those results. Thank you very much.
Thank you.
Okay, we have.